All right, let's go ahead and get started. I'll hit the record button here.
Recording in
Oh,
progress.
hello, everyone, and welcome back. We are continuing on with the MHF4U course. This is the grade 12 University Advanced Functions, and we are in Unit 2, Lesson 3, Part 1 of 2. So we have two parts to the laws of logarithms. And for today, we're going to be having a look at the following topics. The exponent laws review. We're going to be talking about rational exponents. Since I had some questions last time about, can you do a couple more examples of rational exponents? No problem. We're going to be having a look at the product, quotient, and power law of logarithms. We'll actually be doing a proof, which will be exciting for us. Don't worry, it won't be too bad. And then apply these laws of logarithms. On the lesson of next time, we're going to be solving logarithmic equations involving the quotient and product to logarithms. And so we're going to reserve the more technical component for tomorrow. And we'll know things have gone well because you'll be able to use the product, quotient, and power law of logarithms. And so to start us off for today, I should also mention that I have the Desmos graphing calculator and the Desmos scientific calculator. Mostly the graphing calculator I have because that is a log-based whatever button in case it comes up. Okay, so if you want to convert between a logarithm and an exponential, so if you have, say, log base a of b is equal to x, that's the same thing as a to the power of x is equal to b. Again, an important component for evaluating and simplifying these things down. Okay. With respect to the exponent laws, you might be wondering, why are we learning about the exponent laws? Well, recall that for logarithms and exponential powers, that they are considered inverses of each other. And so because the exponent laws exist, there will be an analog in the land of logarithms. So I thought it'd be a worthwhile exercise for us to review the exponent laws. And here's a small little review for us. The product rule of exponents says multiplied by a to the power of c. That's the same thing as a to the power of b plus c. And so action, if you have 5 to the power of 3 multiplied by 5 to the power of 6, keep the base of 5, add the exponents. So 3 plus 6 is equal to 9. The quotient rule, if you have a to the power of b divided by a to the power of c, or if you happen to see the division variant with the beyond or division sign, you keep the base and subtract the exponents. And so if you have 4 to the power of 5 divided by 4 to the power of 3, that's the same thing as 4 to the power of 5 minus 3, and that'll be 4 to the power of 2. Lastly, but not leastly, if you have the power rule of exponents, that says if you have a to the power of b to the power of c, you just multiply the exponents, so it'll be b times c. So 7 to the power of 4 to the power of 3 is the same thing as 7 to the power of 4 times 3, which is 7 to the power of 12. And this extends into higher values as well. So suppose you had something like 7 to the power of 4 to the power of 5 to the power of 6. This is the same thing as 7 to the power of 4 times 5 times 6, which would be 7 to the power of 120, which is some large number. So, okay. And so the other component that we want to look at are rational exponents. So again, if you have a to the power of 1 over n, that's the same thing as the nth root of a. And so on your calculator, the nth root is this button right here, kind of n above the square root. And if you have a to the power of n on m on n, that's the nth root of a to the power of m, or the nth root of a all to the power of m. Typically, this is a much more useful version of the exponent of the rational exponent law, because it's a lot easier to think of that number than to evaluate the other way. And an example will show why we prefer to use this method. Okay. The first one here is 49 to the power of 1/2. That's pretty straightforward. That's going to be the second root of 49, which is the same thing as us saying the square root of 49, which is saying what number times itself gives you 49. So you can use a calculator to assist you with that, or you can conclude at 7. Okay. What about 16 to the power of 3/4? Well, one way to think about this is the fourth root of 16 to the power of 3. So what number times itself 4 times produces 16? That'll be 2 to the power of 3, which will be 8. And again, I can confirm these things using the calculator. So if we do the nth root, so the fourth root of 16, you can see we get 2, and 2 to the power of 3 is equal to 8. Again, I can use the calculator to evaluate just the whole thing. But I wanted to show the process for how this works. Now I mentioned, and so you can see here I lined up in the color coding this, I could also use the second method. And so the reason why I'm hesitant, would not want to do it that way, is because if I was to evaluate the same thing, 16 to the power of 3/4, done as the fourth root of 16 to the power of 3. And already I have a problem because I don't know what 16 to the power of 3 is. And so that ends up being 4,096. And then you have to ask yourself the question, what number times itself 4 times produces 4,096? And if you're not familiar with your 4,096 table, that might be kind of difficult. But using the power of the Desmos calculator, we can see we get the same answer of 8. It's just that it requires much more brain power in order to solve this. So we do prefer using the blue method, namely evaluating the index or the nth root business first, and then taking the power afterwards. Okay. And so I have a little review section here, or a learning section, I should say, on the laws of logarithms. And so since logarithms are the inverse of exponentials, a similar set of rules for simplifying logarithms exist. And so our restriction on this is if we're dealing with things of the form log base a of x, we make the stipulation that a is greater than 0, because again, we can't take the log of a negative number. That doesn't make any sense. And we also make the restriction a cannot be equal to 0, which I exemplified down below. And so here, the product rule of logarithms says log base a of x times y is this is log a of x plus log base a of y. And for clarity purposes, if we had, say, log base 3 of 8 plus log base 3 of 5, we keep the base, log base 3, and we go 8 times 5, which is 40. And you might have noticed some of that, the way I spoke is similar. We keep the base. That was true in the case of simplifying exponential powers, where if you were looking at the product power or quotient expressions, you needed to keep the base and do something with the exponents. Here, something similar, but we're just affecting the argument. Okay. What about the quotient rule of logarithms? Well, if you have log base a of x over y, that's the same thing as log base a of x minus sign log base a of y. And so if you wanted to simplify this down, you could say log 80 minus log 20 is the same thing as log of 80 over 20, which is log of 4. A calculator can also be used to verify this is the case. So if on my calculator here, let's go log. So if I take log of 80 minus log of 20, you can see I get this 0.6 number. And if I type in log of 4, I get an identical number. So we can verify via a calculator that the laws of logarithms are holding. The most useful property is the power rule of logarithms. And it says that log base a of x to the power of n is equal to n log a of x. And so if you have log base 7 of 8 to the power of 10, that's the same thing as 10 times log 7 of 8. Note that this is not the same as us saying log base 7 of 8 and to emphasize this, we're not saying if this is to the power of 2, this is not the same as 2 log base 7 of 8. We're saying that the exponent is only affecting the portion inside of that bracket. Okay, so just note that there's a difference between these two things. And if you remember as an observer from last time, the inverse property we ran into was that if you had, say, log base a of a to the power of x, this was just equal to x. The reason for this is because if we were to bring down the x, we'd have x multiplied by log base a of a, but log base a of a is 1. So this ended up being x times 1 is equal to x. So x is equal to x. Okay, so these were some of the log properties that we learned about on the lesson of last time. Okay, additionally, if we were having a look at log base 1 of 50 is equal to x, so because sometimes I got asked again, why can't you have a base of 1? Well, if you you would end up with 1 to the power of x is equal to 50, and 1 cannot be raised to any power to produce 50. That's just not going to work. Okay, that does not make any sense. So that's why we have to have a base not equal to 1. And in truth, if you had the base was like, say, 0.5, this would have a solution. In that case, your exponent would have to be some negative number. So if we had, say, log base 0.5 of 50, we could evaluate this as log of 50 divided by log of 0.5. Oh, let's get our log calculator in here. Here we go. So log 50. And here you can see we end up with some negative number. So there's nothing wrong with numbers between 0 and 1, and from 1 to infinity, well, approaching it. The issue was specifically at 1. Okay. So with that, I wanted us to prove the quotient law of logarithms. So here, we want to, and again, in the textbook, we proved the product law of logarithms. So I thought it'd be worthwhile to prove not the thing that I already proved in the textbook. So let's prove the quotient law instead. And we're going to make stipulations. We're going to say that we're dealing with logarithms. We're going to say that a must be greater than 0. And when I say, I also mean capital A to be little a, just because it's easier to show these things. My little a's inevitably look like 9, so this is a small consideration for me. And we're going to say that a cannot equal 1. And again, that's for the same reason we said from above. We would run into this situation where 1 to the power of something has to equal a non-1 number. Okay, so let's get started. So we're going to start off by saying let a to the power of n equal to x and a to the power of n equal y. So for clarity purposes, we're going to say a to the power of n is equal to x. And then the logarithmic interpretation of this would be log base a of x is equal to m. By a similar token, if we run into the situation where a to the power of n is equal to y, then we could say log base A of y is equal to n. So already you should be looking at these as if we were making progress, because if you notice, our answer is supposed to be a log base A of x and a log base A of y, and we appear to have two of those already. So let us begin. Okay, so first thing we want to do is, since we're talking about quotient, it would make sense if we divide these things. So here, let's take x divided by y. Well, what is x supposed to be? Well, x is supposed to be this a to the power of m business. So we'll write this down as a to the power of m. Now, what is y supposed to be? Well, y is supposed to be this a to the power of n. Okay, so if I take x divided by y, that's the same thing as a to the power of m divided by a to the power of n. So our first step here is to divide x by y. And they're equivalent. Okay, next thing we need to do, well, x to the power y, not much I can do there, so I'll just write down another x divided by y. But if we have this a to the power of m divided by a to the power of n, notice that the bases are the same with different exponents. So we can write this as a to the power of m minus n. So here what we did was we simplified the exponential. What we need to do now is convert this to the logarithmic equivalent. So note that this will be log base A of x over y is equal to the exponent, m minus n. So this was our logarithmic equivalent. So what happens now? Well, if you notice at the start here, I already have an expression for m. M, we said, was log base A of x, and n was log base A of y. And so we have log base A of x over y is equal to m, we said, is the same thing as this log base A of x. And n was the same thing as log base A of y. And in fact, that will be our proof. You're done. So we go ahead and give that a nice little box. And we are finished our proof. So we'll draw a little box down here and shade it in. And this just says that we are finished the proof. Well, I guess I can't erase that, so let's try doing that again. And there we go. Okay, so this proof was able to work, and all we had to do was start with our statement from above. So we said, let a to the power of m equal x, and let a to the power of n equal y, stating that with their logarithmic equivalent. And then we were able to just run through the algebra. You can use similar techniques to prove the product, and then later, if you so wish, you can also prove the power law of logarithms in a similar manner. Okay. And so from above, I just want us to, we're going to go ahead and simplify some of these down. And I just wanted us to, and as a point of review for you, remember the common powers for chart from before that'll come up, as well as the same properties. And again, the properties here are worth mentioning again. The inverse property was, we said that log base a of a is equal to 1. The logarithm of the same base was log base a of a to the power of x is equal to x. These should be reversed, but that's okay. I'll go ahead and change that in the notes. The power rule of logarithms, log base a of x to the n is equal to n log base a of x. The product law says log base a of x times y is equal to log base a of x plus log base a of y. And the quotient rule of logarithms, which we just proved, was that if you had the log base a of x divided by y, that's the same thing as log base a of x minus log a of y. And we're going to spend the rest of the lesson now just applying these rules and properties to various simpler numbers before tomorrow, where we apply this to more complicated expressions. Okay, so example 3, and I think we go all the way down to j, so we've got 10 examples. We're going to express the following as a single logarithm and then simplify it. And so I started off with 2 examples of basic ones that we had studied before, namely, if you have log base 8 of 8, that's just 1, because log base a of a is 1. And if you have log base 7 of 7 to the power of 4, that's equal just to 4. Okay? And the longer explanation is multiplied by log base 7 of 7. Log 7 is 1. Okay, so now let's apply some logarithm laws. So letter C, if we have log base 4 of 2 plus of 32. Okay, first thing we want to do, we notice that these are both base 4, and so we can write this as log base 4 of 2 multiplied by 32. Keep the base, multiply the arguments. So this becomes log base 4 of 2 times 32 is 64. 64 is the same thing as 4 to the power of 3 and this will then just be equal to 3. Okay, so our goal is to be able to reduce down the logarithms like how we did yesterday, where we are able to just express with a common base and then be able to solve it. It's not so interesting when we try to evaluate these if we have to use a calculator. So we try to choose ones where we can work the skill of trying to find a common base. Okay, what about log of 5 plus log of 4? Well, this will be the same thing as, just a moment. Oh, sorry, and a big sneeze there, and you didn't want to hear that on the microphone or audio recording. Okay, so we have letter D here, log of 25 plus log of 4. Only thing, remember, is that if you have log x, that's the same thing as log base 10 of x, okay? So now we end up with log of 25 times 4. 25 times 4 is 100. And we know 100 is the same thing as 10 to the power of 2. And this is going to give us a solution of 2. At this point, notice that they are base 10. So if you wanted to so choose, you could just type in log of 100. But again, we wanted to evaluate this using the laws of logarithms. Okay, so log 25 plus log 4 is the same thing as log of 25 multiplied by 4. which is equal to log of 100, which is the same thing as log of 10 to the power of 2, which is just 2. Why stop at 2 logarithms? What about log base 6 of 4 multiplied by log base 6 of 3 plus log base 6 of 3? Well, we can simplify this down to be log base 6 of, and then take 4, multiplied it by 3, multiplied it by 3. So if you're not sure, 4 times 3 is 36. So this will be log base 6 of 36, which will then become log base 6. 36 is the same thing as 6 to the power of 2, so our solution is going to be 2. As a note, if you have log base 6 of 3 plus log base 6 of 3, that's the same thing as 2 times the log base 6 of 3. And you might be saying, well, that somehow made it worse because we were able to get rid of one of the logarithms, but now we have something in front of this. But remember, we can apply the power law of logarithms to make this log. And I just want to give myself some space here. You can make this log base 6 of 3 to the power of 2, which is going to be log base 6 of 9. And then 9 times 4 was 36. So just note that you can run into these a little bit of an unusual circumstance where if you have log 6 of 3 plus log base 6 of 3, you actually have 2 logs base 6 of 3. So these are just some little nuances that you can do with logarithmic algebra. And again, I would be remiss if I did not make mention that you could do this. Okay. And you might be thinking, why am I allowed to do that? Well, keep in mind, log base 6 of 3 is just some terrible decimal, right? And so if you have if you have a strange looking decimal plus another strange looking decimal, you actually have 2 of those strange looking decimals. And we can continue. Okay. What about log base 2 of 80 minus log base 2 of 5? Well, that's a quotient. So we keep the log base 2, we divide the arguments. So that'll be 80 divided by 5. Oh, not 4, that's 2. 80 divided by 5 is 16. If you're not sure about that, you can always use a calculator to help you out. So this will be log base 2 of 16. 16 is merely 2 to the power of 4. This will become 4. Okay, so log base 2 of 80 minus sign log base 2 of 5 is the same thing as log base 2 of 80 divided by 5. So that'll become log base 2 of 80 divided by 5, which is 16. 16 we can rewrite as 2 to the power of 4 and simplify using our inverse property. And again, I do make a big deal about the fact that you really do want to spend some time and commit this chart to memory, just because, again, these powers for logarithms occur frequently, and it is a good investment of time to just be familiar with these, or be thinking, if one of my numbers is 64, then I should be thinking that I can write that as 2 to the power of something, 4 to the power of something, or 8 to the power of something, and all those will be acceptable. Okay. What about letter G? We have log of 40 plus log of 5 minus log of 2. We can actually combine these all into a single step. And so you could write this as log of 40 multiplied by 5 divided by 2. And so if I take 40, multiply it by 5, divide it by 2, I would get 100. And since we're dealing with log, no base, so it's base 10, this is the same thing as log of 10 to the power of 2, which is going to be just 2. Okay, what about 20? For h, we have log base 7 of 245 plus log base 7 of 1/5. No problem. We can make this log base 7 of 245 multiplied by 1 divided by 5. And remember, you don't really need to write that multiplied by 1. This is just helpful for your notes because what if the number had been, say, 6/5? And then you would just, in that case, take 245, multiply it by 6. And then at any rate, 245 times 1 divided by 5 is probably 49. Because otherwise I would be surprised that this question makes its way in. It sure is. So 49. So log base 7 of 49 can be rewritten as log base 7 of 7 to the power of 2, which will just be equal to 2. Okay. And now we've got letter I. 3 log base 16 of 2 plus log base 16 of 32. So we saw this earlier. In this situation, what we want to do is apply the power law of logarithms, which says that if you had n times log base a of x, that's the same thing as log base a of x to the power of n. And so, consequently, if you have 3 times log base 16 of 2, that's the same thing as log base 16 of 2 to the power of 3 plus sine log base 16 of 32. So just be careful here. This is 2 to the power of 3, so that's going to give you 8. Don't think of this as 2 times 3. This is a common mistake I see students make, so do try to avoid that one. So we can rewrite this as log base 16 of 8 plus log base 16 of 32. 8 times 32 is 64 times 4, which I think is 256, but we should just double check that. Yes. So this is the same thing as log base 16 of 8 multiplied by 32, which will be equal to log base 16 of 256. And you may not be familiar with your 16 times table, but 16 times 16 is 256. And so we can write this as log base 16 of 16 to the power of 2. And so our answer to this is just going to be 2. Lastly, but not leastly, what we have next is a few of these things. So now we've got 1/2 log base 3 of 225 minus sine log base 3 of 5 plus sine 3 log 3 of 3. I recommend at this point, go ahead and pause the video. If you're watching this on YouTube, try this out for yourself and see what you can come up with. Okay, so let's see how we did. So first thing you want to do is to go ahead and move the exponents back up. So this 1/2 will be applied to 225, and this 3 will be applied to the other 3. Actually, in this case, we don't actually want to do that for the second one. The reason being is we have log base 3 of 3. That's just going to be 1. So this will just be a plus 3 at the end. So we don't really need to include that part in. Just like I said, sometimes like I said, if you didn't do that, you could still include it in. Your answer would just be slightly larger. Okay, so this will be log base 3 of 225 to the power of a half minus log base 3 of 5. And we can just plus 3 afterwards. So this expression, this log base 3 of 3 is just equal to 1. So 3 times 1 is just merely 3. Okay, the square root of 225 is 15. So this becomes log base 3 of 15. Because remember, if you want to take the square root of 225, that's going to give you 15 minus log base 3 of 5 plus sine 3. Let's simplify using the quotient rule. So we log base 3 of 15 minus log base 3 of 5 is the same thing as log base 3 of 15 divided by 5 plus a 3 afterwards. 15 divided by 5 is 3, so this becomes log base 3 of 3 plus 3. We run into another log base 3 of 3, so that's going to be 1 plus 3, which will equal 4. Okay, so again, a lot of steps in this one, but some of these can be simplified down. I'm showing you every single possible step in order for you to save time with these things. Okay, how are we doing for time? All right. I think we've got 2 pages left, so I think we're on track so far. Example 4, the textbook has a couple of these questions that they just want you to practice. We don't need to simplify these things. We just merely want to be able to work with logarithms and be able to write them as either a sum or a difference. So for question number Roman numeral I, they want us to write the following as a sum of logarithms. And so for all of these ones, we need to find, not using shapes, but we need to find 2 or more. We're going to stick with 2 because that's going to be easier. Numbers multiply to give the argument. Okay, so what 2 numbers multiply to make 20? 5 and 4. So we can break this up as log base 3 of 5 times 4, which becomes log base 3 of 5 plus sine log base 3 of 4. So we just want to be able to work backwards. So what 2 numbers multiply? So for the letter B, we have log base 7 of 45. Any 2 numbers that multiply to make 45? How about 9 times 5? Sounds good to me. So we can write this as log base 7 of 9 times 5, which will become log base 7 of 9 plus sine log base 7 of 5. Great. What about 90? And you might be asking at this point, can I just use 90 in 1? You could, but then we would end up with the situation of log base 5 of 1, which is 0. So that wouldn't be a sum of 2 or more logarithms anymore. So try to choose numbers that do not give you something trivial. So here, for 90, why not choose, say, 9 and 10, perhaps? And so this will become equal to log base 5. Now, instead of 90, we're going to write 10 multiplied by 9. And so this will be equal to log base 5 of 10 plus sine log base 5 of 9. You could have also, instead of 10 and 9, you could have chosen, say, numbers like 45 and 2. And that would also sufficed with respect to a suitable answer. Again, you just want to avoid the boring case of the number in itself because you didn't really get anywhere. Okay. This red solution I listed off is an alternative solution you could have written. You could have also done like 3 times 30 would have been great, or 15 times 6, or a further division of those. Question letter double I, or Roman numeral 2, write the following as a difference. And so remember, difference meant a subtraction. And the book does lay out examples like this. So for letter A, we have log base 2 of 72 divided by 35. So you can just break this up immediately as log base 2 of 72 minus sign log base 2 of 35. It seems trivial, but the book just wants you to realize that these are fractions that can be broken up. Okay. Letter B says 2 log 4 of 10. Now, you might be thinking, and you would be correct, could I write this as 4 log of 4 base 10 minus sign 2 log base 4 of 10? And that would be absolutely correct. Because keep in mind, I mentioned earlier when we had log base 3 of 3 plus log base 3 of 3, that was really 2 times log base 3 of 3. And so in this instance, we have the equivalent of, say, 4 minus 2. Or if you want, you could write this, be a little bit more clever. You could write this as, like, say, 6 minus 4 if you wanted to. And that would also give you 2. Now, if you didn't think of that, which is completely reasonable, you could instead, what you would want to do is to move the 2 using the power log back up onto the 10. So we would make this log of 4, log base 4 of 10 to the power of 2. 10 to the power of 2 is 100. And now we need to think of any 2 numbers that divide to give you 100. You kind of pause and think for a moment there, and you might think, what about 1,000 divided by 10? And that would work out just fine. So then you could write this as log base 4 of 1,000 minus log base 4 of 10. And admittedly, it's a much more difficult to think of the difference of logarithms because trying to think of 2 numbers that multiply to make 20, 90, or 45 is much easier than thinking of numbers that divide to give you 10. But alas, the book does have you practice these. Lastly, but not leastly, what about log base 3 of 8? So what 2 numbers divide to give you 8? I'm taking 16 and 2. So you could write this as log base 3 of 16 divided by 2, which becomes log base 3 of 16 minus sign log base 3 of 2. So again, decent practice. Okay, last example is just 2 questions, and it's finding an approximation using a given condition. So here, they're given that log base 2 of 7 is this 2.8 number, 2.8074. They want us to find an approximation for log base 2 of the square root of 7. And so when they give you a question like this, they don't want you to just type this into a calculator. Okay. The reason why they're giving you a question like this is because they want to ensure that you are capable using the laws of logarithms. They're saying that at some point you need a log base 2 of 7 in here, and then you can make an appropriate substitution. So in this case, if we have log base 2 of the cubed root of 7, well, that's the same thing as log base 2 of 7 to the power of a third. So here we convert to a rational exponent. And now using the power law, we can bring down the 1/3 in front. So this becomes 1/3 multiplied by log base 2 of 7. So this is the power law of logarithms. And now look, we now have a log base 2 of 7. Well, that's that 2.8 number, right? So we can rewrite this as 1/3 multiplied by 2.8074. And this is okay. This is an okay spot to use your calculator because now you're just saying what's 1/3 of 2.8074. So here it's okay to use a calculator because again the textbook knows that you know what you're doing at this point. And so we would write our solution as 0.9358. If you really wanted to, you could work that out by hand, but I think we'll leave it like that. Okay. Lastly, but not leastly, we have letter B. Given that log base 2 of 5 is this 2.3219, find an approximation for log base 2 of 20. And so already you should be thinking of this fact. Well, we need to either find a product or a quotient that somehow uses the 20 and the 5. And so we need, you can think about it, 5 with something equals 20. So in this case, most people are probably thinking, we just go 5 times 4, and that'd be what we do to solve this. 4 has the incidental benefit that if we write this as log base 2 of 4, we can actually evaluate that as a using a common base. So here, what we're going to start with is log base 2 of 20, and then we're going to rewrite this as log base 2 of 5 multiplied by 4. And so that'll give us log base 2 of 5, which we have a decimal answer for, plus sign log base 2 of 4. And I'm just putting brackets around the numerical part of the logarithm just because I find it easier to track. Okay, so log base 2 of 5, we said was this 2.3219 number. Log base 2 of 2 is the same thing as log base 2 of 2 to the power of 2. So we end up getting 2.3219 plus sign just 2, which is going to give us 4.3219. So log base 2 of 5 times 4, we rewrote as a, I guess we could be a bit more precise. We rewrote 20 as 5 times 4. Next, we used the product law of logarithms. So we broke up the log base 2 of 5 times 4 into log base 2 of 5 and log base 2 of 4. Next, we evaluated log base 2 of 5 as the condition. And then we also used a common base And then we just added the two numbers together at high speeds using the power of computation. Okay, so with that, that's going to end our introduction to the laws of logarithms. As a good exercise for yourself, I would ask you to go ahead and prove the product law of logarithms. That's something you should be able to comfortably do now. Recall earlier that we had proved the quotient law, and a number of the key questions you should be now able to do. On the lesson of next time, namely the next one in the series, we're on class number 6 tomorrow, we'll be looking at solving logarithms that involve variable exponents. So we're going to end up with both linear and quadratic terms. The textbook only asks us to solve for quadratic terms, but I felt it necessary for us to review linear terms as well. So for now, if you have any questions, comments, or concerns, please feel free to reach out and we'll get back to you as soon as we can. But goodbye for now, and we'll see you next time.